Hi there, I'm Stephan Lavavej, and welcome back to part 4 of Core C++, in which we continue exploring what happens when you call a function. In part 1, we saw name lookup. In part 2, template argument deduction for things that are templates. Part 3, overload resolution. And now part 4, virtual functions, when you have a member function that happens to be virtual. And I'll also be talking a little bit about access control. So you can see here I've got Visual Studio 2012 RTM, or VC11 RTM, installed on my laptop, because this supports a couple of C++11 core language features, override and final, which I'll be looking at while we're in the neighborhood of virtual functions. And let's see. OK, so let's get started. I don't need this demo program here. So in previous parts, I've mainly focused on just talking about the machinery of C++, a little bit of philosophy, especially when it came to explicit template arguments on function templates, where people are often tempted to sort of help the compiler along, but really you want to avoid helping the compiler. In this part, with virtual functions, I want to talk a little bit about inheritance. Inheritance is certainly useful, but it's far from my favorite feature in C++. Because it can be easily overused. I find that I prefer to use inheritance in a certain very restricted set of circumstances when I want to do things at runtime that would otherwise be impossible. But I certainly don't use it every time I want to do things like code reuse or genericity. I will use inheritance when I need to, but it's sort of the last thing in the toolbox that I reach for. It's definitely not my first resort. Other languages and even other styles of using C++ are very different. But I prefer to avoid getting into the sort of situations that inheritance can lead to. When you've got large class hierarchies with lots of base classes and tons of virtual functions, I find the code sort of tends to accrete or snowball, where you end up with these hugely bloated classes with hundreds of data members, hundreds of functions, some virtual, some non-virtual, and it becomes extremely difficult to figure out what's going on. Something that I think a lot of people don't appreciate is that when you have one class derived from another, you're creating an extremely tight coupling between those classes. The relationship between a base class and a derived class is really the second closest relationship that classes can have in C++, the closest being friendship, where the classes know everything about each other. With the base and derived, it's almost that bad, where a base class needs to know that it's going to serve as a base class. It has to set things up for the derived class. And then the derived class needs to know everything, almost everything about the base class. It needs to know what functions to override, how the base class is going to use them, how people are using the base class. So I will use inheritance, but I don't want it to sort of take over my program. Not everything is an object. I get a lot of work done just with plain old functions, or classes that are not intended to be used as base classes. They're just ordinary classes. Object-oriented programming, to me, means that I'm using objects to encapsulate both state and behavior. And if I want inheritance, I know where to find it. But I certainly don't need to be using inheritance all the time. So one thing that we've seen in C++ so far with name lookup and template argument deduction, overload resolution, is all of this is happening at compile time. It's happening statically. Whereas virtual functions, they behave, their behavior has effects at runtime. And so this is, we're all familiar with something like you got your class base, and it's got stuff in it. It's got a virtual destructor. It's probably non-copyable because we don't want slicing. And then we've got our class derived. And it derives publicly from base. So if you read the standard, and again, this is such a complicated topic that it deserves an entire clause. The standard only has 30 of these in C++11. Clause 10, derived classes, where virtual functions lives in 10.3. When you have something like a base star p, and let's say we're going to new up a derived. Of course, I'm saying new here, so this is probably a leak. So I should be using unique putter, shared putter, but I'm just going to talk about the core language for now. and then I'm going to give it some args or maybe just default construct it, whatever. So the standard has the notion that if I call something like p arrow meow, okay, the so-called static type of p is base star. So the static type of deref p, here I'm just going to write an expression without actually doing anything with it. The static type of that is base. And by static, the standard means that the compiler sees that deref p is a base, so you can only call things that are in the class definition. That's what the thing inside the braces there. You can only call things that are declared within base. However, the standard has a separate notion that the dynamic type of deref p is derived, because at runtime, what it really points to is derived. So the machinery of virtual functions says that, okay, an ordinary function will be invoked according to the static type of the expression used to call it. So if meow is not virtual, then it's going to invoke base meow, which of course has to be declared. But if base meow were declared to be virtual, then its implementation will be selected according to the dynamic type of whatever the expression is. In this case, it really points to derived. So if derived has overridden meow, then that implementation will be selected. That's just virtual functions 101. So there's a lot of trouble you can get into with virtual functions. In fact, the trouble is sort of impossible to enumerate, certainly in 50 or so minutes. So I'm not going to get into all the problems you can get into with hiding, and what if you have virtual base classes, which are extremely complicated. But there is a sort of classic gotcha that C++ 11 has a new tool to deal with, and this is unintentional hiding, when you don't actually override something you thought you were supposed to override. So here I've got an example. Let's take a look at this. I've got, after including all the headers I need, I've got a base class here called shape. Shape is very simple. I have given it a virtual destructor, and I've made it non-copyable. I guess I can talk a bit about slicing. So one of the things about C++ is that although it's got the notion of base and derived classes, and it's got virtual functions, inheritance can be used outside of the traditional way of, okay, I'm going to have a pointer to a base class, I'm going to have it really point to a derived class, and then everything that I invoke there will be virtual or end up in a virtual call. It really doesn't care. C++ just lets you do whatever you want, and it's up to you to use it in a comprehensible manner. And especially when it comes to inheritance, C++ does not really guide you into doing anything. Most things are done by convention. So it's certainly possible to use inheritance without virtual functions at all. And in fact, this is done like even within the STL as an implementation detail. Like Vector really does have a base class. No, it doesn't have any virtuals. That's just for our convenience. And one of the things where C++ lets you do something is, imagine I've got a class base. I often mention this to programmers, they're like, slicing, what's that? And yet it's really important to know if you're ever doing anything with derived classes. So imagine I've got a class base, and I give it a constructor, and I've got a virtual destructor because I'm trying to be careful, because I intend to delete it through pointer to base. And then maybe I've got some cool data member, int b, and then I've got a class derived, public base, and then I've got some cool int d here, and I've got constructors that'll set these up and functions that'll use them. If I literally write this, but I don't take any steps to make base non-copyable, then the compiler says, oh, you've got a class here, and just like you can copy structs in C, I think you should be able to copy this class too. So if you haven't declared a copy constructor and copy assignment operator, C++ says, oh, well, I'll generate one for you. And then derived will also be copyable. And this sets up something actually really bad. So nothing here is stopping me from, imagine I've got a, let's see, how do I want to do this? Imagine I've got a base star p is new derived. Okay. So here everything's working fine. I'm newing up derived, storing it to pointer to base. And then I do something like, okay, I've got a base b2, and I'm going to say deref p, like this. So this will compile, and it will do things at runtime which are probably not expected, because what happens is that base gets a compiler-generated copy constructor. I guess I can write it in red here. That looks like base from const base ref. Everybody knows what a copy constructor looks like. In C++11, it'll even have a, no, strike that, it's got a destructor. I think the rules there are special. But it's definitely got a implicitly generated copy constructor. So this will compile, and it says, okay, you're trying to construct a base from some expression. And I see this copy constructor here taking const base ref. So the type of dref p, oh yeah, that's a base. I can totally bind a base to const base ref. And what will actually happen is that this implicitly generated copy constructor will slice. It will only copy over the derived part of this thing that, it'll only copy over the base part of this thing that actually is derived. So if it's got cool derived members, those are just gone. And if it's got cool derived functionality like virtual member functions, that's also gone. You only get a copy that's now actually a base. This is true even if I originally had a pointer to derived. If I said derived here, okay, now the type of dref p is a derived, and yet I can still copy it. It says, oh, okay, you're constructing a B2, and I see this copy constructor. Can I bind a const base ref to a derived? Well, yes, I can, because a derived is a base, so I can certainly bind this reference to the base part of derived. Again, you get slicing. Slicing is essentially never desirable. I don't think I've ever seen a case where you would want slicing. So essentially, rule number one of polymorphic base classes is you want your destructor to be virtual, so the correct destructor gets invoked. If you don't mark this as a virtual, then you'll just leak random stuff in your derived. And it should be non-copyable and non-assignable to prevent bogus code like this from compiling. One of the things about C++ is it loves value semantics, so it loves to copy your objects. We've seen with C++11 move semantics that helps efficiency by avoiding unnecessary copies, but the tendency to want to do either copies or moves is still there. So unintentionally copying polymorphic base classes is extremely undesirable. Please lock it down. Make your classes non-copyable and non-assignable. So here, because we don't have defaulted and deleted member functions, I'm declaring them as private and unimplemented, so that locks that down. I've got my virtual destructor. I've got a very simple virtual function here, draw, and just for instrumentation purposes, I'm printing out that this is a derived implementation of draw. It says shape draw and then x and y and whatever. So the way that this is used is then I have a derived class polygon. A polygon is a shape, and it's going to inherit this, it's going to have a virtual destructor. It's also going to be non-copyable, so I don't need to deal with any of that here. And it's going to override draw. And it's going to say, okay, I've got this derived implementation, polygon draw. So that's all cool. Let me skip over this code here. And if I have a polygon, here I'm going to use the STL to avoid any leaking. I can construct a shared putter to it using make shared, and then I can store this in a shared putter to shape. So this behaves just like saying shape star equals new polygon, except it's exception safe, it won't accidentally leak. Look, no new statements, no delete statements, no nothing, and yet everything will be freed properly. And if I call shape draw here, I can even put a breakpoint and compile this. And it's compiled. And yes, I get polygon draw invoked because even though the static type of dref shape would be shape, it's pointer to base, it's going to invoke this virtual function and invoke the derived implementation. So everything is cool. Now I put this breakpoint here. Let's see what happens. I've also got this other class. Let me hide this a bit, which I've called the evilgon. The evilgon is also a shape, but maybe it doesn't have straight sides. Maybe it's like wobbly. And here I've said virtual void draw, and I'm trying to override this, and I haven't looked too closely at my base class. So I said that, hey, this thing takes doubles, because maybe my coordinates, I don't want, integer coordinates, I want doubles. And then I'm going to print, oh, I'm the evilgon implementation of draw. So I really want this to be invoked. If somebody invokes draw with either, 3344 or 3.14, 2.7, whatever. And yet, I didn't get the types right. I said draw takes two doubles and returns void, and in the base class, draw takes two ints and returns void. So this will compile. C++ lets this compile. and yet it won't do what I want at runtime. Remember how I said inheritance has tons of gotchas. So if I then continue execution, I am going to make a shared evilgon, and I'm just going to assign it to my shared putter to base, shared putter to shape here, and then I'm going to invoke draw on it. So the intention of the programmer who wrote this busted code is that I should get evilgon draw printed, and yet that is not what will happen if I continue down here. Instead of evilgon draw, I got shape draw, and it prints 3344. So it compiled, but it did the wrong thing. This is immensely scary. People often love to sort of bash template errors. They're like, oh no, our template errors, they're terrible. They're like, 1,000 lines, they're like a novel, War and Peace. And yet to me, yeah, template errors can be confusing. But they're nice in that they prevent code from ever compiling. You don't ever ship something to customers and then find out, months or years later that, oh, it was really broken. It fails to compile on your dev box, and then you figure out what's wrong, and then you fix it, and everything is good. Things that explode at runtime are scarier, because without testing, you'll never know if they were broken. And because inheritance and virtual functions, they work at runtime, they open up lots of opportunities for things like this to happen. So the rule here, which is somewhat well known, is that if you have a function, and yeah, you mark it as virtual, but the signature does not exactly match that of a virtual function in the base class, you don't get this virtual overriding. So here, what evilgon has is something very strange. It does have this shape here where it's got this virtual void draw taking 2 ints, but then it's also got this completely separate function draw that's hiding the base implementation that takes 2 doubles. So if I'm invoking something through a pointer to base, then that little bit of magic that says, oh, really invoke the derived implementation, that hasn't been hooked up properly. So I get the base implementation invoked. I could write other code that would show that this draw taking doubles here is hiding, but the code is already bad. I'm not getting overriding. So in C++ 98, there's no way in the standard to prevent this sort of code from compiling. You have to just be very careful to always make your derived signatures match your base signatures if you want overriding to happen. But C++ 11 now has something called Vert Specifiers that allow you to lock this down. So the base class in C++ 11 remains unaffected. I declare draw exactly like this. Then when I am attempting to override it in my derived class Polygon, let me terminate the program. OK. So after the signature of draw, where I would put like const specifiers, and this will totally work with const as well, I can say override. And I've got caps lock on. And override here is a context-sensitive keyword. So if you want, you can still have ints named override or whatever. But between this parenthesis and this opening brace, there's no way in C++ 98 to put something like override here. So C++ 11 says, yeah, OK, if you put override here, it's not a keyword, but I'm going to treat it as one. And it's going to have this special meaning. So this will compile, and everything will run as before. It won't affect Polygon at all. But if you mark a function as override, like here, that does not, in fact, override a virtual base function, then it will fail to compile horrifically, which is exactly what we want. We're already getting a squiggle from IntelliSense, and this says, error, member function declared with override does not override a base class member. Well, that's nice. And if I attempt to compile, I'll also get that. It'll say build failed, and why did it fail? It says 3668, evilgon draw, method with override specifier override, did not override any base class methods. So when you announce that a virtual function is overriding a base implementation, or base signature, it could be pure virtual, it's a promise to the compiler. You're saying, if I'm actually holding up my promise, then OK, don't affect the code at all. But if I break my promise, actually go check. And if it's not overriding a base declaration, then deterministically fail to compile. The standard says that a diagnostic is required in this case. The initial specification of override involves C++11 attributes. It was really ugly. They fixed it just in time to use these context-sensitive keywords. So this is very nice. Essentially, if you are writing C++11 and you're writing a virtual function that you know is overriding, if you just mark it as override, now you know that this evil gone situation can't arise, and that you're not going to get accidental hiding. So that's nice. C++11 also introduced another context-sensitive keyword called final. And this allows you to lock down inheritance in another way. And we can take a quick look at that. Let me get rid of the if0 here. And again, because it's a context-sensitive keyword, if you have code that's saying in final, then that's totally cool. It's only if you put it in these specific places that it gains this magic meaning. So here, imagine again, I've got a shape, exact same as before. It's got a virtual void draw. I've got a polygon, and here I'm just using override. Final and override, they can be used together. They don't have to be. But in this case, I'm just going to say override. Then I've got a triangle that is also a polygon. OK, and it's got a draw. And then I've got a Bermuda triangle down here that derives from triangle. So imagine that once I get down to this triangle part of the hierarchy, I'm like, OK. You know, a triangle's a polygon's a shape, but I want to lock things down, and I don't want anybody to derive from this class. In C++ 9803, there's no way to prevent somebody from deriving from a class. So there's nothing stopping, maybe, you know, triangles in a library somewhere. There's nothing stopping a user from saying, oh, my Bermuda triangle is a triangle. And yet, if the class author decides that this doesn't make any sense, they have no way to stop this from compiling. In C++11, they do. So in triangle, here I can just prove that it compiles. And yes, build succeeded, and let's pretend we didn't want it to succeed. So I can mark the entire class triangle as final. It goes out, I've got to insert on. I can mark the entire class triangle as final, and if I put final here, this says, okay, I'm going to promise that, yeah, final, it's a class, maybe it has some base classes, but nobody can ever derive from it. So if somebody does attempt to, like this evil Bermuda triangle, I get a squiggle, and it says error, final class type cannot be used as a base class. The actual compiler will also complain. It'll say cannot inherit from triangle as it's been declared final. That's nice, so I can lock down an entire class. The final keyword can also be used in another place. Imagine that I didn't mark the whole class as final, but I say, okay, I've got this class triangle, and yeah, people can derive from it, but I've got this one implementation. And whether or not it overrides anything, I don't want anybody else to attempt to override it. So here, I could put final here. And I'm going to promise that although you can derive from triangle, you cannot attempt to override this particular member function. So here you can see Bermuda triangle is not being squiggled, but draw is. It says cannot override final function, and it even points to the line where it's declared, and the real compiler will also complain, function declared as final cannot be overridden. So you can either lock down an entire class from being derived from, or a particular member function. And like I said, override here, sort of bystander. You can say, this thing is final, and yes, I'm overriding, but they don't necessarily go together. I could declare it as final, and I don't need this extra override check. This will still prevent draw from compiling. Even if it says, hey, I'm trying to override, doesn't matter. The base class triangle here has said, this is final. Interestingly, final can also open up optimization opportunities for the compiler. Imagine that you've got triangle here, and either the whole class has been marked final, or this particular implementation of draw has been marked final. If the compiler sees a pointer with static type of triangle star, and somebody's calling draw on it, and it sees, oh, this thing has been marked final, or the whole class is final, it knows at compile time, statically, deterministically, that nobody can be attempting to be overriding this thing. So it doesn't actually have to use the whole virtual call machinery of v pointers and v tables. It can simply directly call the function, and that can be a candidate for inlining. Actually, the overhead of a virtual function call, it used to be like a big deal, like back in the 80s. Now it's barely detectable. It's like, you know, it's in the nanoseconds, if that. However, the fact that if you're trying to call a virtual function and you don't know what implementation is going to be selected, that prevents unconditional inlining. That's actually a really big deal. Whereas if you're using final and the compiler can just skip that virtual function call, then it's a candidate for inlining, and that can actually be really good for performance. Beginning in Visual Studio 2012, or VC11, the optimizer now has this machinery called devirtualization, where if you've got a virtual function call and the optimizer can prove that it can really only hit one particular overrider, then it can just devirtualize the call and call the specific implementation that it knows will be invoked, and it's a candidate for inlining. But devirtualization is not magic. There are things that will prevent it from working, especially if you've got a lot of derived classes. And even if it speculatively devirtualizes with final, if you can just unconditionally do that, that's even better. So that's C++11 override and final. Now what I wanted to show is all the different ways that we can use virtual functions and misuse them. There's a particular pattern that I like to use, and that's called NVI, or the non-virtual interface idiom. There's a second way that I like to use inheritance, and that's for type erasure. I covered that at length in my Going Native 2012 presentation, ST11 Magic and Secrets. You can find it on Channel 9. Shared putter and stood function in the STL use type erasure internally. They just sort of magic away a particular type that you give it, and they erase either the signature, the exact type of a functor, while retaining only a signature, or they erase the fact that a shared putter was constructed with a custom deleter, allocator, or even make shared, which is an enormously powerful and not even that advanced technique. So I won't get into that here, but I will cover NVI because it's sort of the most structured way that I've found to use inheritance. So actually, I can keep my shape class here, because that's nice. So, yeah, I'm going to keep polygon. So what does NVI look like? So here, where I've demonstrated that I've got shape has a virtual function draw, and then polygon here is just directly overriding it. This is sort of traditional inheritance. I've got a public virtual function in my base class, and then the derived class also has a public virtual function that's overriding the one in the base class, and then the derived implementation is selected. That's nice. This is sort of unstructured. Shape could have other virtual functions, and if I've got a derived class polygon here, I'm sort of restricted to matching this particular signature, taking 2 ints and returning void. But within draw here, I could do anything. I could print out whatever I want. I could, have network calls, database calls, whatever I want. And the shape base class has no way to do sort of structured work around it. Whereas with the NVI idiom, we can provide more structure. And again, it's completely a convention. Nothing in C++ requires you to code like this, but it's a pattern that you can follow. So the way that NVI looks is, instead of having a public virtual function, I have a public non-virtual function. And here I could say shape draw, and I can even say that this is non-virtual. And then I can call a virtual function doDraw with x and y. And I can even do things afterwards. I could say shape draw says bye. Okay. And then privately, I'm still non-copyable and all that. I'm going to have a private virtual function. And at this point, I could mark it pure virtual, which I usually do. I just say equals 0 here, saying, hey, you definitely need to override me. I could provide a default implementation if I wanted. There's not that NVI doesn't really care whether you provide a default implementation or not. I traditionally like to say pure virtual. And why am I getting this here? Oh, because I need to say doDraw, not draw. There we go. So I could mark it pure virtual. Or provide a default implementation. That's up to me. Here I'm just going to demonstrate pure virtual because that's how I usually use this idiom. And then in Polygon, I derive from shape, and then privately, I say doDraw here. And then here I can say, okay, Polygon, I'm actually doDraw. I could call it doDraw whatever I want. It just needs to have a different name. And then do print out x and y. And then within main, I could say, okay, I'm going to have a shared putter to base, just to prove that I'm invoking it virtually in the end. SP, and I'm going to make shared a polygon, and I'm going to say SP arrow and draw. And of course it's not called base, thank you, it's called shape. There we go. And let's see what happens here. And I need to pass arguments. Duh. 1729. Okay, so it compiles, it runs, and look what happens. So we've got the share putter to the base class shape that really points to a polygon. I've invoked draw with 17 and 29. So draw is a non-virtual public member function on the base class. This is where non-virtual interface gets its name. And this here has an opportunity to do work either before or after calling this other function doDraw. And here I'm going to print that it's non-virtual, and then afterwards I'm going to print by, and that's what I get. I say non-virtual and then by here. And then I call this helper function doDraw. So doDraw here is private and virtual. Nobody outside of shape and its derived classes needs to know anything about doDraw. So I could have a default implementation here. Here is just pure virtual. And then this actually invokes at runtime any derived class implementation doDraw here. And so I get polygon doDraw printed out in the middle. I'm also not restricted to just doing things optionally before or after. I could also do something to the arguments. Maybe somebody is passing in degrees of rotation and I want to convert that to radians before calling doDraw, or I want to permute or add extra arguments or do whatever. This outer function, the non-virtual public member function, has an opportunity to do whatever it wants before calling this structured virtual function doDraw here. I could also be calling multiple helper functions. I could call doRotate, doDraw, doShade, doRender, whatever I want. And all of these specific derived implementations, if they're all virtual, would be invoked. So I like NVI because it's structured. It says, okay, I'm going to divide responsibilities here. Shape is going to define how people are going to use this base class. So it's going to say, okay, I've got a draw function taking a coordinate, and that's it. People can't go customize me to do completely ridiculous things. And I'm going to do some setup work, maybe some teardown work, other sort of structure. And then I'm going to call a little virtual function that will allow derived classes to actually provide whatever magic they need. So maybe Polygon will, draw line segments. We could have a shaded object that'll go invoke some shader on the GPU, whatever you want. Or, a circle where a circle has a certain radius. The derived class is going to take care of doing this specific magic in here, but it doesn't need to know what the common functionality in the base class is doing. So I could do work here, like I said, converting units or whatever. So something here, whenever I show NVI, people are often confused. Let me shut this down. They're often confused by the fact that I can mark the virtual function here as private, and then I can override it here privately as well within Polygon. They're like, wait, how does that even work? Because Polygon can't directly call this base function here. And the answer, it's sort of subtle. There is this principle in C++ and good design in general that things, when they're orthogonal, it's easier to understand them. Orthogonal is this sort of nerd term. It means like sort of perpendicular. It means that things they don't know anything about each other, and yet they can be used together. So in this case, access control and virtual functions, they're orthogonal. Whether something overrides or not has nothing to do with access control. So in the long saga of how a member or a function or a member function is invoked, access control is applied surprisingly late. I mentioned that I would talk about this just a little. So after name lookup and optional template argument deduction and overload resolution, when the compiler is going to statically call some function, it applies the access control check on a member function. Am I actually going to be allowed to call this thing at the very end? It happens after overload resolution. This surprises a lot of people. They're like, I've got this private function, so I don't want anybody to see it. So how come overload resolution is selecting this private function, and then access control comes in and says, wait, you can't actually call this thing, it's been marked private or protected, you don't have access to it. And this is actually a design decision in C++. It could have been designed the other way, but by putting access control essentially at the end, what this means is that the access control of a function can be changed, from either public to private or private to public without affecting overload resolution. If you think about it for a moment, it would be very strange if you changed a member function from public to private or vice versa, and then that went and invoked a completely different function at runtime. Whereas with C++, as it is specified, if you change the access control of a function, you can make the program not compile at all. But if it continues to compile, then you'll still be invoking the same function. This is more predictable. So that's why access control is applied at the end of all the static checking that the compiler does. But once access control has been applied, then the virtual machinery powered by vtables and whatever, that is invoked essentially at runtime without regard to the access control of the base declaration or the derived declaration. So if I've got here, imagine I've got my class base, class derived, and all of the setup here, non-copyable, all that stuff. I'll just put them side by side here. Okay. So stepping outside of NVI for a bit, just to show you what's possible, I could have a public virtual function here, and I could say virtual void, choose a name completely at random, taking no args, nice and simple. And then within derived, I can say also virtual void, and then do cool things. And this, because it matches the exact same signature, it takes nothing and returns void, and it's marked as virtual in the base class. This could either be public, and it will override. This is the case that everybody knows. Or I could mark it as protected, or I could even mark it as private. And it will still override, because access control and virtual functions are orthogonal. This is sort of confusing at first, but if you separate out what the static type of things are and the dynamic type of things are, it will make sense in the end, I promise. If I've got this situation here, which this is not necessarily code you want to write, changing the access control of a derived implementation, I certainly can't think of any reason I'd want to do this. But C++ allows it to happen, so if you ever see code like this, what's happening is that you get this virtual overriding if the base implementation is attempted to be invoked. So if somebody is calling through a base star, meow, then the derived implementation will be invoked. But the access control check is applied statically. So what this means in this sort of setup is if I've got a base star, and say I'm just outside the class, I have no special rights whatsoever, base star p, okay, equals some derived, I can just say that. I'm allowed to say p arrow meow. The compiler will do this check and it says, okay, the type of deref p is base, and you're attempting to call meow, and I see that meow is public, so okay, you have access to this. However, this setup here will prevent this code from compiling. Again, the compiler will say, okay, you've got a new derived, and you are, oh, this brace is coming from here. Compiler will say, okay, you've got a new derived and derived star p, and you're attempting to invoke meow on p. The static type of deref p is derived. Okay, so let's go look up access control. You're attempting to call meow, and wait, meow is private here. So this will fail to compile because the access control check is applied statically. The compiler doesn't even care that it really is overriding this function that's public and that you could invoke it. And in fact, this will compile if you say, okay, I want to invoke meow, but not as through the derived class. I could say static cast, using these delicious C++ casts, as delicious as casts can get, which is not very, because casts are evil. I could say static cast base star of p arrow meow. And the compiler will let this compile. It'll say, okay, you've got this P, it's derived star, but wait, you're static casting it to base, okay, then you go invoke meow. So statically at compile time, now you've got the rights to invoke this thing. So, like I said, it doesn't necessarily make sense to write code like this, but C++ totally lets it happen. Even more confusingly to people is the scenario which I've outlined in NVI. If I've got a private member function in base, then the scenario here is that meow, it's still overriding because the signature matches. It doesn't care. Yet somebody outside base, base itself can invoke meow and overriding will happen, but somebody else outside base cannot invoke it because it's private. And in fact, even within derived, I can't invoke the base implementation. So this actually does have relevance to NVI here. Imagine that I'm back here and I've got shape, I've got my draw, I've got my do draw. Okay. Imagine that I really had a default implementation. Okay. I said something like this, and I'm going to print default shape do draw. I don't need a semicolon there. C++ is slowly starting to infect my English, where I'm just ending sentences with semicolons. Okay, so I've got a default implementation of do draw here. So if I chose not to override it in Polygon, this would be totally cool. I would get the sort of default shape do draw. In this case, it probably doesn't make sense. You know, what does it mean to just draw some generic shape? But you know, C++ will let it compile. And if I mark the base implementation as private, this actually does mean something. It means to this derived class Polygon that, okay, you've got this base do draw. If you do not provide an overrider, then I've got this implementation sitting here that will be invoked. If you do attempt to provide an overrider like this does, then you cannot call the base implementation while doing whatever it is you're doing. So I can say, okay, see out Polygon do draw, but I cannot attempt to call the base version. If I attempt to say base do draw, this is how you turn off the virtual machinery. In C++, if you've got a virtual function, it will really, really want to be invoked virtually whenever possible. But the one thing that will shut it off is if you explicitly qualify the call with a qualified name, base double colon, then that specific implementation will be invoked. So if I attempt to invoke base do draw with x and y, and of course it's not base, it's shape, then I'm going to get a squiggle and it says, error, function do draw is inaccessible. So when I mark this base implementation in NVI as private, it's saying, okay, I'm going to provide a default implementation, but you can't go reuse it. So if you override it, you've got to make a totally new one from scratch. This may or may not be desirable depending on what you want to do. I could imagine scenarios where you want to do this. Alternatively, if I mark this as protected, then people completely outside the class can't access do draw. So it's still NVI. The public one is non-virtual, and all the virtual stuff inside is protected or private, so people outside the class can't see it. But because it's marked as protected, what this means, and these guys here should be private, what this means is that I'm providing a default implementation, and by the way, when Polygon attempts to further customize it, it can call the base implementation as a helper. Maybe there is something about generically drawing a shape that it wants to do as a preamble to invoking Polygon. So here, this will compile. The squiggle went away, and we'll see what happens if I compile and run. When I mark it as protected, so the non-virtual shape draw is still printing out some before and after machinery, and then when Polygon do draw, it can call the base one, shape do draw, and that implementation, that default, gets invoked, and then Polygon do draw can go do its thing. So that's what it means to have either public or protected or private on a base virtual function. Similarly, I could mark this one as public or protected or private. If I've got this private or protected virtual function in the base class, there's nothing stopping me from the derived class saying, oh, by the way, this is now public, and anybody can call this statically on my type. However, that would break the NVI idiom conceptually. The whole point of it is to lock down your virtual functions and not allow other people to directly see them, and just have them called internally. But there's nothing stopping you from writing such code. I really can't imagine cases where you'd want to open it up completely public, but if you wanted to, you could. So that's basically what's going on with the NVI idiom. There's tons and tons of other things you could do with virtual inheritance. I could devote entire series to covering virtual functions, but I won't be doing that anytime soon. Like I said, I do use inheritance from time to time in my own code at work where I'm using it to achieve a specific goal. And one of the scenarios that I like to use is stepping out to the STL just for a moment. What I like is something like vector. Okay, so vector, as we saw way back in Intro STL Part 1, it insists on being a homogeneous container. You can give it any element type you like, as long as you can destroy it and do things like that to it. But all of the elements that it stores have to be of the same type. There's no such thing as a vector of like int and a double and a string. That doesn't make sense. Now there's tuple if you like that. That's a you can think of it as a sequence of arbitrary heterogeneous element types whose length is fixed to compile time, but there's certainly no runtime flexibility to a tuple. It really doesn't make sense to say I'm going to have a vector of like arbitrary stuff. Yeah, you can have like a variant or any like that, but those are specific pieces of functionality. However, sometimes you might want to say, okay, I'm queuing up a sequence of things to draw or a set of monsters in my game or something, and I can describe at a high level what I want to do with these. I want to draw them or whack them with a club or whatever. And at runtime, I want to store specific objects here that will do cool things. So I've got a vector of shapes, but I really want to have a triangle and a polygon and a circle and a Klein bottle and whatever. Here you can mix together templates and virtual functions to achieve this. So you could have a vector of shared putter to shape, like this here, V. And this is a specific type. It's saying, okay, my vector of elements, they're all a single type, shared putter shape, and yet my vector V here looks like this. I've got a bunch of shared putters. This one could point to a polygon. It's a shared putter polygon. This one could point to a circle, and so forth. And so if I've got a function draw here, I could follow the NVI and have a non-virtual member function draw invoking a virtual do draw that goes and does polygon things or circle-ish things. I can just iterate over my vector, maybe using the range-based for loop in VC11, and say, okay, I want all of you elements to draw yourselves. I don't really care what you do. Go do your derived thing, and then get back to me when you're done. So this is how I like to use inheritance in a very structured way. What I don't like to do is say, okay, I've got some base class, and oh, this class looks pretty cool, so I'm just going to extend its functionality and reuse code. And then I've got a huge hierarchy of like 50 different classes all inheriting from each other and 50 different virtual functions. Like if I wanted IO streams, which does that sort of thing, I know where to find it. So I lock down inheritance either that way or to use it for a very specific task like type erasure, in which inheritance is really completely hidden from the user. If I've got a vector shared putter shape, the fact that I'm using inheritance is obvious, that I've got a shared putter to base and it's really pointing to derives. In something like type erasure, if I didn't tell you up front that shared putter internally was using it or std function was, and you didn't think about it too hard, you would never know that it was using inheritance. And yet inheritance is really the only way to achieve something like type erasure. So that's sort of the power of virtual functions. I implore you, use them wisely. Don't go nuts with them. So until next time, if you want to see something else in Core C++, let me know in the comments. See ya.